So after this short discussion about the dates of the exams, I think we can start. I just wanted to reinforce the last slide we saw last time, which was on Thursday, about the structural analysis for a timber truss. Some of you may choose a timber truss for your project, and we saw some advice on how to do the design for a timber truss. I just wanted to remind you one important thing, that when we analyze a timber truss, we should take into account also the effect of the connection flexibility. So the fact that the connection is not rigid. So of course this connection here is already regarded as a pin connection, but it's a pin connection with some axial flexibility due to the fact that the bolts or the dowels, in general the fastener that we use to connect the wood itself, have some flexibility. So strictly speaking, you see this is the model that we usually adopt. For example, when we calculate by hand, just another reminder that, as you can see, the regulation allows us to consider an eccentricity between the diagonals and the axis of our static scheme. However, we shall always make sure that the axis of our static scheme lies within the width of the member. Okay, if you remember, this is what we said last time. So we can then solve by hand the static scheme, find out the axial forces, and then we have to take into account that there is an eccentricity. So when we do the design, the strength verification, we shall check not for only axial force, but for axial force coupled with bending moment. So the bending moment comes from the eccentricity between the real axis of the member and the design axis. Okay? So, strictly speaking, this is the model we should consider, where those springs here takes into account the flexibility in shear of the fastener. Okay? And we saw there are some formulas to calculate the stiffness of those springs. Now, the important thing just to keep in mind is that in terms of ultimate limit state design, there is no such a big difference between this scheme here and this scheme here. So in other words, when it comes to design for ultimate limit state, we can use this scheme without any problem. Okay, because we won't find a significant difference in axial forces if you ignore the flexibility of the joint. However, when it comes to do the serviceability limit state checks, then it's very important to take into account those springs, because otherwise we're going to underestimate the actual deflection of the structure. We're talking about underestimation up to 50%. So it means that if we don't consider this kind of flexibility here, and we just consider this scheme here, we just need to keep in mind that the limits that we suggested last time should be increased by at least 100%. We should double it. We should halve it. So if the limit is 2 centimeters, according to this table that I gave you before, if you don't consider this, you need to lower this to 1 centimeter, because otherwise we are going to underestimate by far what is the actual flexibility. Okay? We also saw, if you remember last time, now we don't have time to go back, there is also a way to calculate the flexibility, so the deflection of a truss system like this, taking into account the springs, using the principle of virtual whirling, okay, that you know quite well from mechanics and structure. You remember last time we saw a method to calculate this by hand without any need to use, for example, sub 2000. Obviously, with sub 2000 it's not a big problem, because with sub 2000 you can schematize the whole system quite simply. Then you need to go in all of these joints, and then you need to use the end release function. Because by default, sub 2000 would basically consider all those joints as rigid. They need to click on the joints and say end release for each member. So you need to release only the degree of freedom of rotation, okay? And then you should add, or you can also add this, the flexibility of this spring if you want it with sub 2000. So it's not very difficult to do it using sub 2000. Okay, is that clear? Okay. Now, just a short example of a pitched truss structure. You can see here we have in plan we have some bracing, cross bracing, which is the most used kind of bracing system. Then you have the normal trusses, so 1, 2, 3, and 4. So we have some. You see the top and the bottom chords, and then you have the diagonal member. If you remember, we said last time that it's important when we model a system like this, it's important to make sure that the axes of our static scheme are basically coincident with the axis of the top and the bottom chords. So we shouldn't have any eccentricity here. We are allowed to have some eccentricity only in the diagonals, not in this top and bottom chords. Because you see, those are actually continuous, so we shouldn't take any eccentricity into account. Okay, so in this case, you can see this is a small truss system. The posts, here the columns, are basically made of round wood, which is fixed into the foundation. So in this case, we have a kind of fixed restraint here. So you see that perpendicular to the plane, so out of plane, there are also some other truss systems running perpendicular to the plane. So sorry, perpendicular to the plane. And those systems, those truss systems, have a very important function. The function of those systems is basically to prevent out-of-plane flexural buckling of those truss systems. Also, the truss system may suffer from, let's call it, out-of-plane buckling, like Lugar beams. If we want to prevent this out-of-plane buckling, it's very important, it's very crucial to provide some lateral restraint. One way to provide lateral restraints is basically to have some truss system that runs perpendicular to the plane in order to make sure that those main trusses cannot buckle out of plane. So those are the perpendicular truss systems. This is a photo from outside, and here you can see the main trusses. So those are the main trusses, and then those are the secondary trusses, the one that runs perpendicular to the plane. And the function of which, as you can see, is to provide some lateral restraint in order to make sure that those trusses cannot buckle out of plane. You can also notice that in this case, the kind of connection between the different members is nailed plates or punched metal plates. So those metal plates that are basically inserted, are pressed onto the sides of the members in order to get the connection. You can also see here above the bracing, the in-plane bracing made of plates, steel plates. Another detail, bracing, in-plane bracing. This is the main truss system. As you can see in this case, this is made of basically sawn timber, so not wood, but sawn timber. I would say that this is a typical example of pitched truss that we can find in the Anglo-Saxon countries. So this is taken from New Zealand, but very similar you can find in UK, for example, in Ireland, this kind of countries. In our country, we'll never find something like this. So, also because you see these metal plates, they're not very nice from an aesthetical point of view. And for a structure like this in Italy, we would make it out of timber if we want to have a nice looking. Of course, something like this is not very nice looking, so we wouldn't find this kind of structure specifically. But this is very, as I said, it's very common commonly used in all the former UK countries, former British countries like the UK, Ireland, Australia, New Zealand, Canada, also US. So here you can see the main truss, 1, 2, and then you can see 1, 2, 3, and 4 trusses perpendicular to the main trusses. And the meaning of those perpendicular trusses again is to restrain laterally the top chord and the bottom chord. So to avoid that the top chord and the bottom chord may deflect laterally and may rotate torsionally. Again, remember that for this business here, the major problem in terms of buckling is out of plane buckling, which means lateral torsional buckling. In order to avoid lateral torsional buckling, we need to provide some restraint. Now, I would ask you, why is not enough, for example, here to put only one member? We need to put the whole truss system, your opinion. So what would be enough to put only the bottom chord, for example, rather than to have the bottom chord, the top chord, and the diagonal for this, let's say, additional bracing system, which are more than bracing system are actually systems aimed to prevent lateral torsional buckling. So, what could you tell me as an answer? Suppose I want to limit only, to have only one member here, running 1, 2, 3, and 4. Why is this not enough? Would that be enough to... Okay, so this is the truss system. Another one is here. Another one is here. So why would it be enough to have a system like this to prevent the out-of-plane buckling? So, any comment? Let's try to understand why, because this is crucial to understand, what kind of lateral restraint we can or we cannot use in the system, because otherwise we will make huge mistakes if you don't understand that.
Perché non è applicato al baricentro e non si può applicare al baricentro perché è un sistema a tre luci.
So what you are saying now is that this one is not applied into the center of gravity of what? Of the truss system, which is here.
But we cannot apply with
No. But suppose that I apply this. So why is this not enough to prevent everything? So you can prevent the torsional buckling. Just to remind you that first of all, we should prevent the displacement of the compressed side. So going there is not very clear because we are on the tensile side. So first of all, I would say the first comment on this proposal of mine would be, okay, rather than here, perhaps you should think about it here. Because this is the compressed part, not the tensile part. So this one would be better. But would that be enough? Now, let's try to think about this. Would that be enough? No, why not? What would happen? Suppose that this starts buckling here. Suppose this starts. So, do you remember what is the kind of deformed shape for out-of-plane buckling? So, lateral torsional buckling. You also, I think, you studied also stability dislocation structure. So, what kind of displacement is going to happen if this truss starts buckling? Yes, but in this plane here, what kind of displacement can we see? So, lateral, okay, we will have, of course, we will have some vertical displacement for sure, but for the other displacement would be something like this, and then something like this. Okay? Now, why is this not enough? Because this is a kind of pin connection here. So this is buckling. So suppose we start buckling. Then this one cannot prevent. This one can only act as a truss. So cannot prevent the rotation first. And it will just transfer this kind of deflected shape to the other. So in the end, you would have a global sort of buckling. Global buckling. So you will have all the trusses will buckle simultaneously out of plane. That's why one member is not enough. So in order to make sure that we prevent this rotation, what we have to do, we have to have one member which has not only axial stiffness, but also bending stiffness. So a truss system like this, in some way, as a global truss system, not only provides lateral stiffness, but also rotational stiffness. Because of course, once you do a system like this, now there is no way that this can rotate freely. I mean, this could rotate only if this one is going to distort, it's going to deform too much. So the reason why we have this truss system across the main truss systems is basically to provide some axial stiffness and rotational stiffness. Only the rotational stiffness can prevent this kind of out of plane lateral torsional buckling. Is that does it make sense? Is that clear? Not so much. Yes or no? So. To think about a system like this, to have this kind of you would have to have this kind of distortion here, and to have this kind of displacement, this truss system should distort like this. So in the end, it's very complex, particularly if you use members which are stiff like this. So some other photos about this system. This is a kind of connection between the pole here, again with this tooth and metal plates between the pole and the top chord and bottom chords. The photos. And here you can see the connection between these plates used for the bracing, for the in-plane bracing system and the nodes, and so on. Okay. So I think now, if you don't have any further questions, I think we can move to the next presentation. And now we move to single-story buildings, to this other important chapter about multi-story timber buildings. This is a very important, of course, and exciting chapter, because until I would say 10 years ago, nobody would have talked about multi-story buildings. We would just think about single-story industrial buildings, swimming pools, commercial centers, malls, and so on. However, from, I would say, at least 10 years on, timber has been used also to construct quite a big construction, quite a big building, so multi-story timber building. As you will see, there are some examples now of construction up to 16 stories made of wood. So it's very interesting now to discuss about the techniques, the different structural systems that can be used when we talk about multi-story buildings. So we will start talking about prefabrication. We will see that for multi-story timber buildings, prefabrication is a very important topic. So the idea is that we should think about how to prefabricate a timber building, because this has several advantages, also in terms of cost. And then we will see different kind of structural systems. So we start from log house, which are small buildings. Then we will talk about light frame houses, can be used for small buildings, but also for multi-story buildings. With light frame construction, we can also build up to 4 or 5 story buildings. I will show you also some examples about this. And then solid panel construction, which is nowadays is the most common one, particularly when it comes to very tall buildings. So the use of blue laminated timber and cross laminated timber, moment resisting frames, and hybrid systems, meaning systems where we use different systems of different materials to, for example, for the lateral load resisting system and for the gravity load resisting system. And then I may just mention about buildings, timber buildings with passive base isolation. Of course, talking about passive base isolation will be a significant, more important chapter when you are going to study earthquake engineering, which means next year. But I will just give you I will just mention, because here in L'Aquila we have good examples of passive base isolated buildings made of microscopic. Now, first, if you want, introductory chapter. Why use prefabrication for timber systems? There are several good reasons to use prefabrication. The first one is to improve quality control. So the idea is that if we produce a member in a workshop, we can make we should be reasonably sure that the quality of what we produce is better than the quality that we would get if this construction is done on a building site, as you can imagine. It's much, I would say, it's much simpler to achieve quality control into, I would say, an industrial environment with workers working on the floor rather than on the building site. The building site, as you probably can understand, it's a kind of environment where there are several hazards, and when, of course, it's not the best to walk outside in order to achieve the best quality. So sometimes you can see some mistakes like this, for example. So first, you see that the timber structure is built, and then the electricians come and they cut here and there in order to put, for example, the plugs, the electrical services. In this case, as you can see, one structural member has been cut in order to have room for this electrical system. And this, of course, is not very nice. Or, as you can see here, theoretically, this connection should be, as you can imagine, should be straight on the centroid of the two members. Instead, as you can see, it's not really on the center. So those are typical mistakes that we can find on the building site. Then there is also another good reason to use prefabrication, which is reducing hazards on building site. Some of you may attend this course about the safety of the construction sites, of the building sites. You may all be aware that unfortunately the building site is one of the most dangerous places where to work. Most of the casualties that not most, but a good amount of casualties, unfortunately, and also injuries occurs on the building site. So it's much better if you can move most of the work from the building site to a controlled environment like exactly a factory environment in order to reduce hazards. And then another good reason is to speed up the erection of the building. The idea is that if I'm able to prefabricate, for example, a whole wall on the factory and deliver on the building site, then of course I can save a lot of time when it comes to the building site project or the building. And then also to use technical solutions that should be done only in a workshop. For example, suppose that we want to use glued solutions. So glued between timber and timber, or epoxy glued rod. So glued in rods. This kind of solution, as we mentioned before, should not be done on the building site. Because gluing one piece of timber with another, if you remember, there was an example of a big joint that has been glued on the building site. If you remember, it was like they had to do like a temporary construction in order to protect the environment from the rain. So it's a kind of operation that in general should not be done on a building site. So those solutions you can see here can be done, should be done in a workshop. So eventually we could also say that the use of prefabrication allows reducing the total cost. So it's a matter of money in the end. Prefabrication means having a better solution with reduced costs. Now, think about reinforced concrete. So timber and reinforced concrete. If you think also reinforced concrete buildings in some cases are prefabricated. For example, the floors that you have studied in the course of reinforced concrete design, in some ways prefabricated. So the typical floor solution which is used in Italy is probably not fully prefabricated. I would call it semi-prefabricated. Because if you remember, the typical floor solution, the one we call lateral cemento, with tiles in English, it comes from joists, prefabricated joists, then with some tiles, and then there is a cast in situ concrete. So this is kind of a semi-prefabricated. Of course, you can also have some fully prefabricated solution with reinforced concrete. Think about, for example, solutions for industrial solution, for example, for warehouses or for a multi-story garage. In this case, you have the whole columns and the whole panel are made of prefabricated reinforced concrete. Usually they are pre-stressed, and then the different members are delivered to the building site and connected together. However, reinforced concrete, the full prefabrication reinforced concrete is not very common. Why is it not very common? Because reinforced concrete has an important problem compared to timber. If you remember well, reinforced concrete is much heavier than timber, which means that if you want to prefabricate, for example, the whole panel of a floor, you're going to have one member which is quite heavy to handle. So it's quite heavy to transport, quite heavy to lift, and then eventually to handle. For this reason, fully prefabricated solutions in reinforced concrete are not very common because of the weight. For timber, instead, it's different. For timber, if you remember, specific weight of wood is more or less 1/5 of the specific weight of reinforced concrete, meaning that for timber, we have members that are much more lightweight, and they can be handled, transported, and lifted to position much more easily compared to reinforced concrete. And then for this reason, I would say in Europe, mostly in Europe, also in Italy, the fabrication is used more and more in wood building systems. Now, we start now considering these different building systems, as I mentioned before, starting from low Gauss, light frame, solid panel, monolithic frame, hybrid systems, and with plastic-based isolation. So we start with low Gauss systems. What are low Gauss systems? Low Gauss systems are small buildings that were typically developed on the Alpine region, Italy, Austria, Switzerland, and so on. And they are made from logs arranged horizontally. So in this case, basically, as you can see, the logs are arranged horizontally. On the left, you can see a typical log system made from a real log. On the right, you can see the modern version of the log building, the one that, for example, is provided by producers like Rubner House or other modern producer, where the log, as you can see, is being replaced by kind of glue-lamp beams, always arranged horizontally. So in this case, as you can understand, the wood is loaded from gravity, the load is loaded, the wood is loaded perpendicular to the grade. So all the vertical loads are inducing stresses perpendicular to the grade into the logs, which may seem strange because if you remember that wood does not perform very well perpendicular to the grade. However, we also said that perpendicular to the grade, compression is not so bad. Tension is very bad, but compression is not so bad. But of course, since timber is stressed perpendicular to the grade, we can't really think about, we can't think of building a 10-story buildings in this way. Because it's clear that after 2 stories, the stresses will become comparable with the strength of wood perpendicular to the grade, and then we may suffer with lots of plastic deformation due to the log perpendicular to the grade. So with this system here, we are talking about 1, 2, maximum 3 stories, no more. Because again, of the fact that the wood is loaded perpendicular to the grade, so it's loaded in some way in the wrong direction. So this is used mostly for residential application. What does it mean, residential application? It means that we have to have many walls and short span floors, so not big buildings. Again, I said maximum 2 to 3 stories. And when it comes to seismic design, this means, in this case here, a Q factor, maximum value Q factor will be 1.5, because this kind of building are not really very much specific kind of systems. In this case, as you can see, it's very important to provide this connection between the perpendicular walls. So the perpendicular walls are connected to each other by cutting some notches into the logs and by basically crossing the logs together. We have different kind of details for the notches, as you can see. And what we can say is that to be honest, if you look at the Eurocode 5, you won't find specific formulas, specific exam formulas for those kind of buildings. Those are the typical profiles of the modern log house buildings. As you can see here, this is a kind of it's a 2 lamination beam with this kind of notches. So we have different sizes, possible sizes from 72 to 102. We can also have round blocks. And those beams are placed one above the other. So those small notches here, see it's a kind of notch here, indentation here, like Lego bricks. The idea of these notches are to have a kind of some degree of fixity between one log and the block that we have on the top of this. Of course, for this kind of system, crucial is the kind of carpentry joints between the logs. So you see that those logs are crossing to each other at the corner, and at the corner they are carved in different ways. For example, this is a possible way with this tank and grooves. This is another way, and this is another way. So there are different kind of details in order to get some degree of fixity between the perpendicular notches at the corners, the perpendicular logs at the corners. The floors are usually quite simple. They are made of joists and clamps. And the joists, as you can see here, may go over the wall. So they may have this carving here and go over the wall, or they may just be stopped above the wall with these notches here. Here you can see main log, joist, and another log. This way we can have, again, a degree of restraint between the joist and the main log. In this kind of structure, the idea is that the log-house buildings, the use of metal fastener in general is minimized. So very often who buys this kind of buildings wants to minimize the number of the use of glue and the number of metal fasteners within the building. So, for example, only here you see if the joist doesn't go through, one screw is needed because otherwise we can have, in the case of displacement, for example, in the case of an earthquake, this part here may fall down. So in this case it's important to put the screw. Instead, if the joist can go through, in this case, like this solution here, in this case no screw is needed because this case is a restraint which can prevent the movement of the joint, the falling down of the joint. Okay, now one of the problems with this system here, as you can imagine, since that the system is made from horizontal logs, and since those logs are stressed perpendicular to the grain, is under gravity load the problem of flexural buckling. So why is flexural buckling a problem for this type of walls? Because, again, they are stressed perpendicular to the grain, and perpendicular to the grain, if you remember, the Young modulus of wood is very low. It's 1/30th of the Young modulus parallel to the grain, which is 1/3 of the Young modulus of concrete. Meaning that altogether, the Young modulus of wood perpendicular to the grain is 1/90th of the Young modulus of concrete. So this means that if you remember the formula of Euler, pi squared times E times I divided by L0 squared. If the Young modulus is very low, also the critical Euler load will be very, very low. And then we can expect this kind of failure mechanism. So the failure mechanism under vertical load is flexural buckling, okay? Because again, the Young modulus in this direction is very, very low. So, as you can imagine, having a solid wall in some way is okay, but having some holes, like a door or a window, may create a serious problem. Particularly, as you can see here, in this part of wall. In fact, who is providing some lateral restraint, in some way reducing the flexural buckling, is the connection, this kind of connection between one wall and the other wall. So here it is not shown, but here there is another wall perpendicular to the grain, also here there is another wall. So here, as you can see here, we don't have problem buckling, but here in between, we may have a very serious problem buckling because here we don't have any perpendicular wall providing some restraint. So particularly this part here between the door and the wall, flexural buckling, out-of-plane flexural buckling is a serious problem. How to reduce this problem of flexural buckling? By adding some flexural stiffness within this wall. For example, by adding, as you can see here, a profile, a metal profile. This is basically a kind of rectangular pipe profile, which is inserted, you can see better here, which is inserted on the side of the opening on the side of the window, and on the side of the door. So this metal profile has the purpose of adding a flexural stiffness. A flexural stiffness for out-of-plane buckling. So in other words, in order to buckle out of plane, the wall will have to bend this profile, which is of course is more complex than having no profile at all, so no stiffness at all. So the meaning of those profiles added along the opening inside the wall is to provide some flexural stiffness out of plane, and so to reduce the problem of out of plane flexural buckling. Now, some tests, we performed some tests. In this case, those tests were performed at the University of Trieste. So this is a reaction frame, and these are some jacks in order to simulate the gravity load coming from the floor. And of course, you can see here, this is the wall, one opening, one door, and here there is one window here. This is the reaction frame, those are the jacks. So the test basically consisted in applying a vertical load with these jacks in order to simulate the gravity load and to study the strength of the wall, taking into account what is the problem of the out-of-plane flexural buckling. So you see, with the load, we increase the load, and you can see immediately as you increase the load, this problem of out-of-plane buckling. Then you continue, this is more and more until the end. So the failure occurred here. You can see here those profiles, those steel profiles that are inserted within the wall in order to increase a little bit the out-of-plane flexural buckling. So without those profiles, the strength will be very low. This is another test. This is instead a wall without any hole. In this case, you can see always out-of-plane buckling is a failure mechanism. So this kind of failure mechanism. Then another important problem for this system is how are they able to transfer the horizontal forces to the foundation, so their lateral load resistance. Also in the case, some tests were carried out. Those tests were carried out instead at the IVALS, the Liber Institute, close to Trento. It's a CNR Institute, close to Trento. So some vertical load was applied in order to simulate the presence of the gravity load. So this load was kept constant. So with these jacks, a typical value of gravity load, for example, coming from another floor was applied. And then the horizontal force was increased in a cyclic way in order to simulate the effect of an earthquake. So the best way to simulate the effect of an earthquake is basically to apply a load in both directions, so the cyclic load with increasing amplitude, like in the case of an earthquake. An earthquake, let's say, starting lower, then progressively increasing the amplitude until you get to the failure. In this case, you can see the failure mode was a slipping. So it was a slip within this pillar between the window and the hole and the door. And in terms of resistance, the resistance mechanism here is basically provided within the joint between perpendicular walls. So, suppose that you have one wall and one perpendicular wall, so the load of the perpendicular wall, because of the earthquake, is being pushed in this direction. So who is preventing this load to move horizontally? Basically the contact with this other load. So this perpendicular load could move only if there was a failure for shear into this connection region, or a failure for compression perpendicular to the ground and the contact with the other wall. Okay, now we move to a more common kind of structural system, which is the timber frame houses. Now, timber frame houses are one of the most widespread type of structural system used in all the Anglo-Saxon world. So here we are talking about, again, New Zealand, Australia, Canada, US, UK, Ireland, and so on. In all those countries, I would say that 90% of the most small houses are made of timber. So, unlike in our country where 90% of the small houses are made of bricks and reinforced concrete, in those countries, houses like this are made of timber. When I say timber, I mean timber for both the vertical structure and the horizontal structure. All the small houses like this. Those pictures come again from New Zealand, but as I said, if you go to UK, you find very similar solutions. So, in line frame timber construction, the structural skeleton is schematized in this figure here. So, as you can see, there are a number of walls. The walls are made from studs, vertical studs. On top of the studs, there are some cords, top and bottom cord, called also plates, horizontal plates. And then, this frame made from studs and plates is cladded with sheathing made of plywood or made of oriented strand board, OSB. I would say that in the Anglo-Saxon countries, the best material is plywood, which is used when you have more demanding application, and the worst material often used is particle board, our porcellana. However, in Italy we don't use, it's not very common to find either one, plywood or particle board. So in Italy it's much more common to see the use of oriented strand board, OSB, as a cladding material. So this cladding material, as you can see here, is nailed along the whole perimeter of the frame and along all the vertical studs. So the idea is that we have these panels made, for example, of particle board or OSB or plywood, and those panels are nailed along the horizontal member and along the vertical members. Now, if you take a small wall outside of this structure, and we study better how it is done. As you can see, we said before, we have two vertical studs. So, particularly, we can say we have two outer studs, one inner stud. Stud is I would say in Italian, montante, I don't know what it's called, un montante ligneo. Then we have a top plate and a bottom plate. In Italian, we would call it corrente, superiore, inferiore. Okay? So again, this is a frame with pin connection, and on top of this frame, on one side of both sides of this frame, there is a sheathing panel made, we said before, of particle board or oriented strand board or plywood, and this sheathing panel is nailed onto this frame. So it's nailed along the plate, top plate, bottom plate, and along the whole studs. So if you want, cross-section of this wall will be something like this. One stud, two studs, three studs, and one side panel nailed on the studs. Okay? This is a horizontal cross-section of this wall here. And then, of course, this wall, that now is statically determined, has to be connected to the floor underneath or to the wall underneath, or if you are on the foundation, directly to the foundation. This connection to the foundation is achieved using some bolts along this horizontal member and using some hold down straps. So some pieces of steel, like plates of steel, that connect the outer studs directly to the foundation. Okay? So in the end, what we get, if you want, it's a kind of cantilever system. So this wall, light frame wall, can be considered as a kind of cantilever system, which in the end is fixed on the foundation and must resist vertical loads and horizontal loads, like the loads due to the earthquake or the wind. It's very important to notice that this is the bare frame. In the bare frame, the connection between the studs and the plates is with some nails, like this. Now, what kind of connection is this, in your opinion? This connection between the plate and the stud with two nails arranged in this way. What kind of connection is it? So, it's a pin connection, exactly. It's a pin connection because this kind of connection here cannot prevent any, cannot allow any transfer of bending moment and cannot prevent any rotation. So the rotation is almost free. So a system like this without a shifting would be, the question would be, would a system like this without the shifting be stable under gravity load, under vertical load? Yes or no? Under vertical load, yes. So the system would be stable under vertical load. However, as soon as I apply small horizontal forces, like I displace by, let's say, 1 centimeter, immediately the load will become eccentric, immediately I will have the collapse of everything, okay? Because the system, of course, is unstable under horizontal load. The way to get stability under horizontal load is to use a plywood, or let's say sheathing, and to nail the sheathing along the perimeter and along the vertical stud. Okay? Which one? Which one? Strictly speaking, would be semi-rigid, but much closer to a pin than to a fixed one. Very often, when we talk about joints, very often they are semi-rigid. But we like to classify into either rigid or pinned, depending on whether they are closer to one solution or the other. Which one is much closer to the pin one. So in the end, this system is stable under vertical loads only due to the sheathing, which is in-plane stable, and to the nailing between the sheathing and the frame. Note that the nailing between the sheathing and the frame is actually a semi-rigid connection. Okay, so these nails here between the sheathing and the frame, they are not able to prevent the relative split between the two. So this connection in and this nail connection is semi-rigid, but the total system is stable. Okay? What would be a possible way to make this connection between the sheathing and the frame fully rigid, in your opinion? The diagonal, you mean? So, for example, here, what would you do? To make it rigid. No, to make it rigid. What I'm saying, if I want to make, I said that this nail connection between the sheathing and the frame, it's semi-rigid, it's flexible. So what is a possible way of creating a rigid connection between the sheathing and the frame? Well, we don't have any relative split between the two.
The principal frame.
Okay, here.
The stud.
What do you mean? The diagonal?
No. This configuration.
Yes, this one?
Yeah. Start inside the frame.
Start inside, so what do you mean? To full?
Yeah.
Okay, yes. But in this case, we wouldn't call it anymore light frame, we would call it solid construction. So this is called light frame. Why? Because there is a frame, this one, and because the frame is light. What does it mean light? It's made from small cross-section. Typically, a frame like this would be made by 2 by 4 inches rectangular sawn timber. So 2 by 4 inches is more or less 38 by 80 something millimeter, okay? So 2 inches by 4 inches. So light frame. If I put now other members of wood inside, I don't have any more a light frame construction, but I have a solid construction. And we're going to talk about later on about solid construction. What I'm saying now is what kind of connection between this frame here and the sheathing can be rigid in the sense that I wouldn't have any relative slip between the sheathing and the frame. Among those that we have studied so far. The glued connection, exactly, the glued connection. If I'm going to glue this sheathing to the frame, then I would end up with a rigid sheathing to frame connection. Instead, when I'm using a nail connection, I accept that there would be a degree of flexibility, so a relative slip between the sheathing and the frame during the deformation. Okay? This is very important because also the calculation we see is different. I can tell you immediately that 99% of the cases where you can find a structure like this, nail or staple are used, not glue. So glue is more a theoretical idea, but usually glue is not used. It's used nails or staple. Staple would be in Italian cambrette, which is this. It's like i punti delle spilatrici però fatti molto più grandi. Okay, so other photos. So outer stud, bottom plate, inner stud. Note that the inner stud and the outer stud are supported by the bottom plate. So there is a detail done in this way. Bottom plate, inner stud, outer stud, inner stud, and outer stud. Meaning that if there would be some compression here, this compression will stress the bottom plane perpendicular to the grain. So we see immediately a problem here of compression perpendicular to the grain. Okay? And then you see the plywood shifting on one side. This would be the hold down strap here at the end. So this one should actually connect the stud to the foundation. In the reality, this is not true. I mean, this photo here, you see this metal plate is not a real strap, it's not a real hold down strap. This one, it's a kind of connection done in this way. So if I do a cross section like this, so this is the bottom plate and this is the stud, this connection here is done this way. It's a kind of U plate that simply connects the stud with the bottom plate. So it's not a real hold down. Okay? This is because in this kind of structure used in New Zealand, UK, typically the prefabrication involves only the bare frame. So the bare frame is prefabricated outside. The bare frame, the dell'Aquila, is prefabricated outside. Then it is delivered on the building site. We will see now. Is placed vertically with some temporary bracing, and then it is cladded with the sheathing. Okay? This one. So this is because here I said hold down strap for the sake of simplicity. So this should be the hold down. Instead, in this kind of construction, this is not a real hold down strap. This is a a U-shaped metal plate that goes just around it this way, just a U-shape. It's just made to keep together the bell frame. So you have a bell frame like this, let's say. And this is this connection here. They're just made to take together these elements. So the bell frame is prefabricated outside, then it is delivered on the building side. It is placed, you see, vertically with some temporary bracing. You see this diagonal here. Those diagonal are temporary bracing. Why do we need temporary bracing for this system here? Why do we need this temporary bracing when we construct the system? Because the system is unstable. We said before the bell frame is a non-stable system. So we need to place those temporary braces. So see, it's quite interesting to see how the construction proceeds. So those frames are braced, are placed vertically, and then you see then the whole floor is placed on top of those unstable frames that are still they are still braced, and then another floor is placed on top. Note that the floor is actually squashed between the lower wall and the top wall. This is also called platform construction. Platform construction because we start with a wall, then we put a floor on top of the wall, and then we put the other wall on top of the floor. We continue this way, like a castle of cards. You know the card and another plan, and then you continue this way. You see that in the end there are two floors being constructed with this temporary bracing. Then the next step will be to place the roof. And once the roof is placed and then we are protected from the rain, then we start placing the cladding system. So we start putting the sheathing, nailing the sheathing, and removing the props, removing the temporary bracing. Okay? So this is the way that construction proceeds. And again, just keep in mind this is called platform construction because the floor is in between the two walls. Some way the floor is squashed between the lower wall, the supporting wall, and the top wall. Now, thinking about the static behavior of those walls, there is a significant difference between the behavior of the wall under gravity load and the behavior of the walls under horizontal load. In terms of resistance to vertical load, if we apply a vertical load on one wall, only the wall underneath the vertical load will react. However, if we apply a horizontal force, all the walls, as you can see, will react to this horizontal force. So the walls are all resisting under lateral forces, while instead only the wall which is placed underneath the vertical load is reacting to the load itself. So let's now go to calculate the contribution of gravity load and lateral load. Suppose that one frame, one wall, one shear wall, is subjected to gravity load. Gravity load comes from the floor. We said that we will have some joists with some flooring. Those joints will be above the wall, and those joints will transfer the vertical load N to the wall underneath. Of course, not only the joints, but also the wall which is on top of the joint. So, we said before, in the platform construction, you have a wall, then above the wall you have a joist, the floor, and then above the floor you have another wall. So all the vertical loads here coming from the wall and from the joist will be applied on top of the wall. Okay? Now, these vertical loads, which elements are going to stress? So the cross section of the wall is this one. So suppose that we have some axial forces being transferred. Here I can, on top of these members, we have this plate. So on this plate we have some vertical compressive load applied here. Now the question that I ask you is this vertical loads here, and which members I'm going to stress out of all of this that you can find there? So? The studs for sure. What else? Only the studs, nothing more?
During the construction.
No, after. Let's say after. After everything, after the construction is finished. So the studs will be stressed for compression, parallel or perpendicular to the grain. Parallel to the grain. And what kind of verification do we need to do for compression parallel to the grain? Ultimately mistake. So if we have compression parallel to the grain starts, what kind of verification do we need to do? Buckling? Yes? In which direction? Okay, let's put some axes here. So are we expecting these studs here to buckle in this direction here? So out of plane, or to buckle in plane, in your opinion? Or both?
Out of plane.
Out of plane. Why not in the other direction?
Because in a direction in plane.
In plane, yes.
We have another elements that.
Which other element?
Other walls. Other stud on the walls.
Okay, suppose we have only this wall, no other walls. This is the only wall we have. Okay? So, we are checking, for example, this stud here. Why is this stud not able to buckle in plane? Because there is the sheathing material, sheathing panel, and in order to allow this member to buckle in plane, the sheathing should distort, should deform in this way. While instead the sheathing it's not rigid but has some significant stiffness in plane. So this is absolutely right. So the stud cannot buckle in plane. Why instead it can buckle out of plane?
Because we don't have element that restrains the.
Yes, the restraint the lateral movement. In reality there is an element because the same sheathing is connected with some nails to the stud itself. So in some way, we cannot say it's preventive, but for sure, if this member wants to buckle out of plane, it will also have to deform the sheathing out of plane and the connection itself. But of course, the stiffness out of plane of this sheathing is much lower compared to the stiffness in plane of the sheathing. So for sure, there will be a contribution, but being much lower, we can conservatively neglect it. Okay? It's clear to all of you? So, for vertical load, the only element stressed is the studs, and we will have to check that we said out of plane buckling of the studs in compression. Strictly speaking, however, there is also another stress in some other elements. Which other elements? If the frame is done in this way, which other element do we need to check also? Exactly. We need also to check these members here, the plates, because you see they are stressed perpendicular to the grain. So we have to check here compression perpendicular to the grain and compression perpendicular to the grain on the plates. Okay? Instead, talking about the sheathing, do we need to check the sheathing for something? The sheathing. We need to check for something when we have these vertical loads. Depends on what? No, this way. It's done in this way. In this way, with the sheathing, we said nail all around here. So do we need to check the sheeting for something and the nails for something?
I don't know if sheeting been before.
That's a good point. So your colleague said it depends when the sheeting is placed there. Suppose that first I put, like we saw before, first I put a frame, then I put a load, significant amount, and then I sheet, then I clad everything. In this case, the cladding will be basically without any stress. Instead, if I put the sheeting from the very beginning and apply the load, maybe one part of this will go into the sheeting. It's an important part of the load that will go to the sheeting. Think about the load path. So, longitudinal cross section, you have something like this. You have a stud, plate, and sheeting. So if I apply a load here, do you expect a significant part of this load to go here? No. There may be some stresses, but they are, I would say, minimal. So we don't need to check anything, nails or sheeting for vertical loads. Okay. What about the bolts here in the hold down straps? Are they loaded under gravity load? Again, think about the load path followed by the forces to get to the foundation. So here's the foundation. Here this hold down straps. Do you expect most of this load to go down here? Or just to go through contact, direct contact from the plate to the foundation? They are stressed. So, this one, there is no significant stress going down there. So most of the stress will go by direct contact between the member and the foundation. Okay? Now, let's think about how these lateral shear walls behave when subjected to lateral loads. So we said before that they can be considered as a cantilever. So, cantilever. Subjected to a lateral force. I just would like to use the same symbols. F. Okay. F. Okay, now we said this is like a cantilever. So if this is like a cantilever, of course, we know from static that this cantilever will have to resist a shear force equal to no, the shear force. The shear force of acting on this cantilever is F. And the bending moment M is the bending moment here is F times H. Okay? Now the point is, how can this system resist shear and how can this system resist bending moment? We start, for example, for bending moment. We do a cross section. Okay? Cross section here is 1 stud, 2 studs, 3 studs, sheathing, and 9 connection. Okay? Now a section like this, in your opinion, how can resist the bending moment? this section here is subjected to a bending moment like this. So, if this connection was rigid, suppose for a moment this connection was rigid. If this connection was rigid, a section like this, how can resist to bending moment? Mostly. Suppose that you are back 2 or 3 years ago, you are doing an exam in mechanics of materials, and at the exam you are asked to calculate the stress distribution of a cross-section like this, subjected to bending moment and then shear. How would you solve this problem? Of course, in that case, they would have told you that this connection is not made by this glue. It's like if there was a connection without any discontinuity. So in this case, what would you expect to find the maximum stresses due to bending moment? It is thermal stats, absolutely. So you would say, look, here I have my maximum what? Here, tension or compression? Compression. Here I would have the maximum tension, and here almost nothing. Almost. So I would say, well, this one almost zero. So if you wouldn't remember all the formula, well, probably remember the Navier formula, they're not so complex. But now, if you want to do a less rigorous, let's say, approach, less mathematical, say, okay, look, in a cross section like this, how can I calculate in a simplified way the stresses that I have here and the stresses that I have here in a simplified way? Without using the Navier formula, which means without having to calculate the second moment of error of this cross section, which is a bit complex. Well, you could say, in terms of resistance to bending moment, what I can do, I can ignore for sure this part here, because it's close to the neutral axis, and I can ignore also the web here, because the web doesn't take lots of stress in terms of bending moment. So I can transform this cross section here into a cross section like this. So in a cross section like this, how can you calculate the stresses? Here and there. So I will ignore, as you can see here, I will ignore this inner star and also the whole web. For the sake of simplicity, in order to find out a simpler solution. Not very rigorous, but for our purpose, it's more than enough. So, now, I say, this is now my resisting cross-section. Yes, with equilibrium, which means that compression, tension, so C equal to T equal to M over B. And then, of course, sigma equal C divided by A, the area of one of these, or T divided by A. Okay? Not sure if with a solution like this you would have passed the exam of mechanics of material. Probably not. But for our purpose, it's more than enough. Because we have so many approximation before and after that having an approximation here like this is not going to change too much. Also because you see, the reality, our cross-section here, we said it's not glued. So we don't have a cross-section which has this shape. We have here mechanical connection, so we don't know how to. So the formula of mechanics of materials wouldn't be rigorous in our case because we have a nail connection which is flexible. Okay, So for us, it's more than enough to find a solution like this. Meaning that we discovered that in the end, for the lateral resistance, so who is going to contribute to the resistance to lateral forces are the two outer studs. One stud in compression and the other stud in tension. The tension and compression can be calculated with very simple equilibrium. So F in the end, M divided by D, which means F times H divided by D. Okay? So this one, C equal to T, is also equal to F times H divided by D. Equilibrium, compression and tension. Okay? Now, compression force. How is going to be transferred to the foundation the compression force? So if you have compression, so this compression force, how can be transferred to the foundation? Which way? So one stud is compressed. Then underneath the stud there is one plate, and then underneath the plate there is a foundation. So through the plate, which kind of verification we will have to do? Again, so again we have to do a verification compression perpendicular to the grain here. And then we have direct contact to the foundation, nothing more. Okay? Do we need to do any control on the hold down strap here, compression? There's also a hold down strap before we say compression. Do we need to do any control for the hold down strap? Compression? Here. This one. Perpendicular to the grain where? In the plate? Yes? Well, no, but now I'm talking about this hold down strap. This one that we saw before. This one. Do we need to do any change? Any check here? In compression? Yes or no? But what did we say before? If I have compression here, do we have a significant amount of compression going down the strap or not? No. So, we don't need to do any check in the strap, at least in the compression part. Now, in the tensile part, sorry, let's go now. Here we have tension, as we said. Here, how can I transfer this tension to the foundation? Fasteners connecting the stud to what? Yes, but with which number? Let's go back again. So here the stud, that this time is subjected to tension. So how can you transfer the tension directly to the foundation? Through which member? Which element? So? Not really, because with the horizontal one is going to separate. And also with the horizontal one, even if I could manage to connect the vertical to the horizontal, then the horizontal would be subjected to what kind of stress? Suppose I glue this to the horizontal one. So they are transferred the tensile force from the stud to the horizontal one. But then the horizontal one is subjected to which kind of force? Which kind of stress? No? I have a detail like this now. I glue this, so here I have a tension, and here. What kind of stress I would have here? Tension perpendicular to the grain. Tension perpendicular to the grain is, what is the test? It's almost zero. So there will be no way that we can transfer a high tensile force through here. So what do we need to do? we need to use this metal hold-down strap. So we need to have a metal bar nailed here, nailed on the stud, which can then transfer the tensile force down to the foundation underneath. Okay? Otherwise, we don't have any way that we can transfer this axial force down to the foundation. It's clear? So, metal strap nailed to the stud and then connecting and taking this axial force down to the foundation, or down to the other floor, or down to the other wall underneath. It's clear? Okay, so in this way, we were able to transfer the bending moment due to the lateral force down to the foundation. But now we need to transfer also the other force, not only the bending moment. We have also a shear force. Now, how do we transfer the shear force down to the foundation? Okay, let's do a sketch here now on this side of the blackboard. So how do we call this one F? We call F this? Yes, F. Okay. Now we need to do some equilibrium. We need to disassemble our panel from the different components. So this is the sheathing. Then within the sheathing we have the nails here, the studs, and the plates. Now let's start from the equilibrium. Equilibrium to the horizontal forces of the top plate. So who is going to prevent, due to the force F, this plate would like to move in this direction? Who is going to prevent this movement? Who is going to restrain the plate there? The shear panel. Actually, not really the shear panel. Strictly speaking, who is preventing? Because who is connecting the shear panel with the nail? So the nails are preventing the movement of this member here to the right. But of course, the nails are connecting this top plate with the sheathing itself. So this means that there will be a distribution of forces here. What kind of forces, in your opinion? How would you define these forces here? What are? Sigma, tau, what kind of forces are? Tau are tangential forces. Strictly speaking, they are concentrated forces in the nail. So each nail is transferring a shear. But we can, since there are several nails, we can also consider what we call a unit, a kind of shear stress per unit of length. So we could say, okay, here I would have a force. Let me check if I have the right. Okay, V. Let's call it V. Actually, I saw in the presentation we find V lowercase. If you don't use the same symbol, please correct V in V lowercase so we don't have confusion with the presentation itself. So this will be V lowercase. This will be B lowercase and B lowercase. And they are consistent with all the presentation. So, shear force per unit length, V. V will be F over B. Okay? Shear force per unit length. And we can assume with some simplification that those shear forces per unit length are uniformly distributed along the breadth. If they are uniformly distributed along the breadth, which kind of axial force diagram we will have in our plate? So now if I want to draw the axial force diagram into the plate. So which value of axial force I will have here into the plate? And? Are you sure it's constant? Let's write down the equilibrium. So this is the member. So, first of all, here, if I do a cross section here, what is the value of the axial force here? What is the value of the axial force here? F. This is F. Okay, what is the value here at the end of the member? 0. So in between? Linear, this one. Because we assume that the V are uniformly distributed, okay? So, this means that if I was now to make a diagram of the V, this would be a uniform diagram. But the diagram of the N, of course, is linear, this way. Okay? Good. Now, V is also the same for the equilibrium. If I have a V on the plate, the same V should be also on the panel. Then, if you remember that the other rule that you studied in mechanics of materials, talking about shear, you remember what is called reciprocity of the shear stresses. So if you want, the fact that the co-shear tensor is diagonal means that the shear stress on this side here, how will it be compared to the shear stress on the other side? So this shear stress that I have here, let's call it V prime on this side. How will it be compared to the shear stress on the top? So, yes, it will be the same. Why is the same? What we call, it's called, I learned as a reciprocity of the shear stresses, or the fact that the co-shear tensor is diagonal, symmetric with respect to the diagonal. Okay, so tau zy is equal to tau yz. So V prime here is equal to V. So on this side, we will have a distribution of shear stresses in this way, and this again, V F over V will be the same. But on the other hand, if you remember, before we have also calculated the value that we have here at the base of the studs. So the value we had at the base of the studs was, where is it? M over V, FH divided by V. So here, T, this is C. C is also equal to FH divided by V. So for the equilibrium, V here, if I now study the equilibrium of this stud, I can write down that the shear here is also equal to C divided by H. Okay? So C is FH over V divided by H. And C divided by H, and you see that I found exactly what we said before. The reciprocity of the shear. So I found out from the equilibrium that actually also here the V prime is the same as this, because it's C over H, so it's F over V. So, how will it be now with the equilibrium on this stud here? How will it be the diagram of the axial forces? So, diagram of the axial forces in this stud. Can you tell me please, how does it start? What is the value at the beginning and the end of the stud? So here you see. Okay? Now we can do the same on the opposite side. Here I think there is, now it's clear, there is very little new thing to say. So here we will have something like this. Okay? And then of course here we will have this all down, tick, tick, and then again here. Now of course an important, now we found out the value of the axial forces all around here, and now an important design value is the value of the shear into an A, because then we will have to design an A. So what is the value of the shear force in one single name here? For example, let's call it with the right symbol. Let me find out what was the right symbol. FBAD. Let's go back. So, FBAD. Shear force, design shear force into an egg here. Will be given by what? Well, we need to know the spacing of the nails. So if the nails are spaced, let's say that the nails are spaced S, we calculated the unit shear, V. So V is the unit shear, so the shear by unit length. If I know the unit shear, in order to find out the total shear in one nail, I will have to multiply the unit shear, which is kilonewton per meter, times the spacing of an nail, which is meter. And then I get kilonewton shear force. V is either F over B. Well, if you look at this nail here, actually it would be C over H, which we said anyway is F over B. So in the end, this would be F over B times S. And if you consider one nail above here, assuming that the spacing is the same all around, also here, we will get the same result. So this one would be V times S, and V is the same. So in general, the shear force of one nail connecting the sheathing with the stud is given by V times S, so F over V times S. Okay? This way we can calculate the shear demand into a single nail. And then to solve, to finish the problem, we still have some bolts here. We have some bolts on the lower, connecting the bottom core with the foundation. If we indicate with S prime the spacing between the bolts, then here F, now let's use the same symbol, I think it's F V E V prime, the one for the bolts. Let's go to see if it's the same symbol so after we don't make mistakes. No, we use the same symbol, okay. Okay, then you will find the same symbol, FVD, to indicate the bolts. This will be V, the shear force, times S prime. So in the end, F over V times S prime. Because again, also here, we have always the same shear going around the shifting panel. So basically, you can see all these forces here are constant. Okay? So in the end, the final solution is obtained by superimposing the two cases of only gravity and lateral force. So, if you remember, the only modification will have to be made on the studs at the end. Because we said that due to gravity force, only the studs and the hold downs in some way are loaded. So, ultimately, the state design of machine walls now, different verification. Top plate. The top plate, now we cancel about the gravity load, but if you remember, the top plate was unloaded under gravity load. So the top plate will be checked in compression parallel to the grain, sigma C0D. So sigma C for compression, 0 parallel to grain, D design, will be given by F, so the maximum force here, over AP, where AP is the cross section of the plate. And this shall be less than or equal to KCY times FC0D. FC0D is the design strength of wood parallel to the grain in compression. And KCY is the reduction coefficient due to buckling, flexural buckling around Y. So if this is a vertical section of our wall, for the same reason that we were discussing before, this top plate can only buckle out of plane, so around Y. It cannot buckle around the other axis, because to buckle around the other axis, it would have to distort the whole sheathing. In other words, to buckle vertically, to have a vertical buckling, it would mean that the sheathing must be distorted this way. This is not possible because the sheathing is very stiff in its plane. Okay? So KCY is the reduction factor due to flexural buckling. If you go and see in the lecture that we had several weeks ago, we were talking about buckling, flexural buckling. Then, outer studs. The two outer studs are one in tension, one in compression. Obviously, you have to remember that in the reality, both of them will be the same cross section. So you will have to design both of them for tension and compression. Why? Because the one that is in compression, for example, for seismic force coming from left to right, may become in tension, the seismic force comes from right to left. So we'll set the same thing. So the compression, the outer standing compression, sigma C0D. In this case, we need to remember we have to superimpose the axial, the compression force coming from the gravity load with the compression load coming from the lateral load. So it would be FH over B, the solution here, or also here, FH over B, plus N. N is the axial force coming from the flow, from the gravity load, divided by AC, cross-sectional area, less than or equal to, again, KCY times F0D. And again, like we were discussing before, it's only the buckling around Y is possible, so the other buckling, not the other one. Okay? Clear so far? Good. Then we have to do the design in shear of the sheathing. You can see here the sheathing itself is subjected to a distribution of shear forces constant along the perimeter. So the shear is constant. If you want, going back to this approximation here, if you have a cross-section like this, if you assume that the connection between the sheathing and the cross-section is rigid, in a cross-section like this, which part of the cross-section is mostly subjected to shear? Question from mechanics of structures. In a cross-section like this, assuming for the sake of simplicity that the connection between the sheathing and the studs is glued, so it's rigid. What would be the stress distribution in a cross-section like this? Can I ask some of you to draw me the shear distribution around here? So for example, what would be here the diagram of the shear? Well, usually you saw a cross-section like this turn 90 degrees is subjected to a shear. So what would be the shear distribution there? I hope I would have to ask the other professor to teach again shear. It would be a bit disappointing, I guess.
Dovrebbe essere 0 all'estremità massima.
Okay, let's try this. So it should be, or it would be, how would we say, it should be 0 where?
All'estremità.
So here, okay, and max where?
Al centro.
What do you mean for center? Here?
Yes.
Okay. Now, here, so if I go from here to here, what kind of distribution would it be? Okay, suppose you have a section like this one, maybe it's easier. Okay, let's put also this one in the middle. This is the kind of section we are talking about. I think I saw that you are able to solve, or at least you were able to solve 2 years ago, much more complex section than this, if I remember well. So, we said here is 0, 0. Then here is maximum. Okay, in between, if I use the well-known Jurasky formula, when I move from here to here, how is it going to change this first moment of area? Jurasky formula says that tau is equal to shear times first moment of area of the part of the cross-section divided by the fiber with respect to the neutral axis divided by J, second moment of area, times T, let's call T the thickness. So here, how does the first moment of area change with this distance here? Linearly. So this means that here, this would be the diagram. Then what's happened? Then we need to, if the thickness was the same, which is not the case here, the thickness is different. If the thickness was the same, I could just do this kind of thing. But since the thickness here is different, and this one is much smaller compared to the other, so if it's smaller, it means that this T is going to reduce. So this is the same, this is the same, this is the same, this is reducing, so tau is increasing. So this means that here I'm expecting to have something like this. And then, as I go down, what kind of variation can I expect to have?
Parabolic.
Parabolic. Where is the maximum? Eh? Yes, are we sure that this is the maximum? Let's see. Yes, it is the maximum, but here you see, strictly speaking, if I go here, the thickness is slightly different here. So I should have something like this. Okay? Because here the thickness, I shouldn't do this actually, I should do something different. But anyway, so this is a kind of diagram. Now, based on this diagram, what is the structural member carrying most of the shear? Is the stud, the inner stud, the lower stud, or the web? Well, the inner stud would bring a significant amount would carry a significant amount of shear. However, you must remember that this is an approximation, because in the reality we don't have continuity here. In the reality here there is the discontinuity, and there is one nail connection. So strictly speaking, we cannot apply the same relationship as in the mechanics of structure, because here we have a flexible connection, we don't have a glue connection, we have a flexible connection. So in the end, what we can do is just say, look, the member carrying most of the shear for sure is the web, and the web here is the sheathing. Okay, so the sheathing is the member carrying most of the shear together with what? The sheathing and which other elements carry the shear? The sheathing plus the connection between the sheathing and the studs. So the net connection. Okay? Like we found here. So in the end, the sheathing panel, I will have to design the sheathing panel for shear. The shear will be F over BD. So BD is the cross section in the end. So BD is the cross section of the sheathing. So I assume that only the cross section of the sheathing is resistant to shear. This is the thickness, this is the width. So F over BD less than or equal to FVD, which is the design shear strength, times also here there is a reduction coefficient. Why there is a reduction coefficient? Because also the shear panel might have a problem of buckling. So the shear panel, if you subject the shear panel to shear, it may buckle in this way. So looking down this cross section, the shear panel may buckle in this way. Okay? This is a kind of plate buckling. Plate buckling, which in Italian sometimes is referred to like imbozzamento. Plate buckling. Okay? So how do we reduce plate buckling? We reduce plate buckling. Also to reduce the plate buckling, we put an inner stud. So if we wouldn't have an inner stud, so if we would have only this, so only the outer stud, then the buckling would be something like this. Or something like this. To reduce the effective length of buckling, we place another member in the center. In this case, we can have, as you can see, the effective length for plate buckling. Okay? So now you can understand that there is an important function of the inner stud. The inner stud, of course, it is needed to transfer the vertical load, but it is also needed under the horizontal forces to reduce the effective length for plate buckling of the sheathing itself. And of course, this inner stud must be connected using some nails to the sheathing itself. In the absence of this nail connection, of course, we would have the effective end would have been halved by the inner stud. Okay? So this coefficient Kc is usually equal to 1. Is equal to 1 if we keep the distance between the studs not greater than 60 centimeters. Usually those sheathing panels are 2 points in the Anglo-Saxon country. They are 1.2 meter by 2.4. So 1.2 by 2.4. In Europe, usually they are 1.25 by 2.5. Okay? So if we keep the distance between the studs, I told you before 60 centimeters, Europe is 65 centimeters because it's actually 62.5, which is 1.25 by 2.5. So if we keep the space between the studs not greater than 62.5 centimeters, usually for this size of, let's say, 1.25 by 2.5, we don't have problem of plate buckling, okay? Okay. Then we need to design the net connection. So as far as the net connection is concerned, FVED is F times S divided by B. There is also coefficient, if you look at the regulation, we'll find also coefficient CI, which is 1, you see, for B over H divided by 2, or this other value B less than H over 2. Usually it's always 1, because usually, as I said before, it's the breadth is half of the height. So it's always this ratio 2, so Ci is always equal to 1. But for the sake of completeness, I just wanted to put it here. So this one shall be less than or equal to FVRD, which is the design strength of one single nail. And then we need to remember that if we have more nails on the same line, parallel to the grain, we need to multiply by NEF, effective number of nails, divided by N, total number of nails, if you remember. For the problem with splitting. Then similar thing for the bolted connection to foundation. So for this bolted connection to foundation, we have FVD, Fs prime divided by B, less than this regulate. This formula is exactly the same for the bolted connection to the foundation. And for the hold-down strap, we need to remember that we have tensile force due to lateral forces minus the axial force due to gravity. So then we have to consider that the gravity force in some way is pre-stressing a little bit, so we can use this difference here. Divided by the area of the strap, less than or equal to the design stress of the steel. And then outer stud tension, stress, design stress parallel to the grain due to tension, again FH over B, which is the tensile stress, the tensile force due to lateral force minus the vertical force due to gravity divided by the area less than or equal to FT02. So design strength parallel to the grain in tension. Okay. I think we have exceeded by 20 minutes our usual limits, but I just wanted to finish this topic here because I think we have to leave it halfway the equation, especially not to conclude. Do you have any question what we saw so far? So basically here we solve the problem by using the equilibrium. So all these solutions are just, if you want, very simplified solution obtained just using equilibrium. So no compatibility, no stress-strain constitutive relationship. So it's very basic, but for our problem it's more than enough. Okay? In fact, in general, those kind of structures are always designed using this kind of approximate equation that we found before. We should make a start to try to finish for today. Okay, so we we saw before how to solve a single unit of wall, and of course this single unit of wall can be assembled in a larger wall member like this. So we can have two units on one side, then there is a door, then there is another unit on one side, and then we can have another smaller unit on top of those one. The important thing is that at the separation you see between one sheeting and the other, there should always be one element. In this case, this is called knocking. So the idea is that the sheeting member should always be nailed around the whole perimeter. So this horizontal member here called knocking, which I don't really have an idea of what could be the translation in Italian, probably doesn't exist anymore for Italian of this. And I don't know if you can check on the internet. No, sorry. So this element here is needed basically just to provide the support for this nailing connection between the sheeting of the lower unit and the sheeting on the upper unit. So this member here basically is not stressed at all. This member is mostly there just to get this continuity of shear flow between this sheeting and the sheeting underneath. Okay? It's just needed in order to get the nailing of the two sheeting across this timber member. So when we apply a horizontal force here, F, then we will get from equilibrium, we will get some shear forces. So the resisting member in shear will be basically 3 units. So V will be F divided by 3D, because 1, 2, and 3 here we have a hole. And then we need to find out the vertical component into the outer studs. Note that in this case, the inner stud, well, in this case we have 2 units, 2 inner studs, and this outer stud here, which is a stud between the 2 units, that is actually not stressed with an axial force due to the horizontal force. So in the end, in this case here we have 2 outer studs and 3 inner studs. And the 2 outer studs, by the equilibrium, are calculated. The axial force is calculated by dividing the bending moment, which is F times H. So F times H is the global bending moment, and the global bending moment is divided by the lever arm. In this case, the lever arm is a 3B because 1, 2, and 3. So it's FH over 3B and FH over 3. So all these forces are in the outer in the outer studs. They are basically the same value and they are opposite. So in the end, to solve a system like this, you always have to consider a cross section at the base of the wall to measure the total length, which is 3B, and then by dividing F by 3B, you get the shear force per unit length, and by dividing the bending moment, which is F times H by 3B, again, you get the vertical axial force. Okay? Just remember in this case the intermediate stud between the 2 units is unloaded. It's not loaded. Only the outer studs are loaded. In fact, as you can see, the metal studs are placed just at the outer to connect just the outer studs to the foundation. Okay? Now, we saw how these vertical walls work. Now we need to see how the floors work. So the floor, as you can see, are made by joists, which are in Italian we translate as travetti. Then we have the flooring panels. So these 2-dimensional panels made again of particle board, oriented strand board, or plywood. And then we have these elements across the joints called blockings, which again I don't know how to translate in Italian, but just this perpendicular solid elements. And those perpendicular solid elements again are needed in order to make sure that the sheathing panel, which has this normal size of 1.25 by 2.5, can be nailed along the whole perimeter. So in the end, if you look at the floor units, in some way the floor unit is very similar to the wall unit. As you can see, the floor unit is a kind of wall unit, which is basically just turned in a horizontal direction. Okay? So what before was the studs, now are the joists. What before was the plates, now are the blockings. And the sheathing, it was before and also now. It's very important that the sheathing panels are basically are alternated in this way you can see here. So the sheath panel, since the joints between two adjacent sheathing is a discontinuity joint. Of course, then we can get the continuity of the forces by nailing. It's a good rule, it's actually mandatory that those sheathing panels are staggered. So they are, in order to get, you see, the joints that are not on the same line. Okay, so they must be staggered in this direction, as you can see here. In this case, I would say that the joist and the sheathing would be mostly loaded out of plane due to the gravity force. So out of plane mainly due to gravity. So this kind of structure here, which has been used for small buildings, can also be used for multi-story buildings. So for multi-story building, as you can see, we have the same kind of structure. So we have a vertical wall acting as a cantilever like before. And then we have these horizontal diaphragms, which are acting as a deep beam loaded in plane by the horizontal forces due to wind and due to earthquake. So in this case, usually when it comes to multi-story buildings, plywood replaces particle board. So either plywood or polyester board are used as a sheathing material for both the floors and the walls. It's also very important, as you can see here, the outer stud of the wall, they must be able to transfer this tensile force due to horizontal load down to the foundation. So it's very important to provide some continuity in order to prevent some possible separation. This continuity is usually provided by steel straps connecting with nails the upper stud with the lower stud through the floor. As you can see, the floor, this is a kind of a platform construction because there is a discontinuity on the floor. So on the floor, you see the stud is connected to the floor and then the next stud is connected to the top of the floor. So this is again what is called platform construction. It's not the best one in terms of static resistance because of course you have timber loaded perpendicular to the grain, but it's the best one in terms of constructability of the structure. Much simpler for the builder to build a platform type of construction than to build what is called balloon frame, which means a frame where the cords, the studs are continuous and the floors are outside, are connected outside on the studs. Now, of course, it's very important to realize or to build, to design the floor in such a way that the floor itself is able to transfer the horizontal load to the vertical bracing. So the shear walls, what we studied before as a shear walls, those shear walls become the bracing system of the building. So the building is braced by shear walls because as we saw before, the shear walls are able to resist both gravity loads and horizontal loads. But of course, you see a floor like this, it's not a monolithic one. It's not what we studied in reinforced concrete design, where we have a monolithic construction. So by construction, by the way of construction, the floor itself was able to transfer the horizontal load directly to the bracing system. Here instead, it's this kind of discontinuous structure. So we have a joist, we have blockings, we have the sheathing, and we have the nails. So we should design this floor here in order to make sure that it's able to transfer the all horizontal loads directly to the vertical shear walls, which are the bracing of the system. So while for reinforced usually we don't check the strength of the floor in plane, because we assume that it's strong and stiff enough to transfer the load directly to the bracing. Probably you remember when you do your design, you didn't check the floor for in-plane forces, you just check the frame, you just check the floor for the vertical floor. That's it. Here instead, since this is not monolithic, here we need also to design the floor and the different components in order to be able to transfer the lateral load to the bracing system. So you need to do more checks in this case, okay? So how does it work? You see here that the floor itself works as a deep beam loaded in plane. So for this reason you see that there will be a deflection. So this horizontal load will have to be able to be transferred directly to the two-bracing system. So in this way, in some way, this one is like a beam simply supported with two bracing and loaded with a uniformly distributed load. So what kind of forces can we expect in a structure like this subjected to these horizontal forces? What do you think? Now we ignore for the time being the vertical load, the gravity load. Okay? For the gravity load it's quite simple. If I apply gravity load, then I will have that the joist will be loaded in bending and the sheathing will be loaded in bending. The nails will be loaded in under vertical load. Which kind of forces do we expect on the nails? Shear due to what? Yeah, but we sure that the permanent load is going to load and shear those nails. Compression. Yes, but compression, I mean, in terms of compression, we could also remove the nails. Suppose that I remove the nail, compression is just due to contact in the end. We have some little bit of it. It's clear that I couldn't do this, but strictly speaking, these nails are not very much loaded. I mean, they may be loaded if we consider a kind of composite structure. So, for example, here we have one joist, here we have one sheathing. So, this could be considered as a composite structure, where we have the top sheathing, kind of a T section. So in this case, they would be loaded if you consider this as a composite structure. But if we ignore this composite action between the two, what do you think is that are those nails much stressed under the vertical loads? So in the end, this system would be what we call in reinforced concrete design, what we call a one-way, two-level system. Because we have, there is here one sheathing, which is some way spanning across the joist, so subjected to bending, and transfer the load down to the joist, and the joist has to be loaded in bending. So those nails, in terms of vertical loads, they are not very much stressed. So I would say that the stress in those nails due to vertical loads is almost negligible. That would be just ignored. Okay? Is that clear or do you have any doubt? Why do you want to take into account the withdrawal of the screw? No, now we're talking about autoplane. For the time being, I was just discussing autoplane, gravity. So gravity, load is going to stress the joist, is going to stress the sheathing, in bending mostly, and shear, And then the question was about the nails. Are they going to be significantly stressed by the vertical load or not? This was a question. No. Vertical load, no, unless we consider composite action. But the composite action is done in this way, is quite negligible. In fact, if you want to achieve a composite action, you need to have like a glued connection or to have a timber concrete composite structure. Now, talking about instead the in-plane action. Now we're going to talk about the in-plane action. So those horizontal forces, what kind of stresses are going to induce in those members here? Can you try to see? So this one works like a simply supported beam lie down horizontally, subjected to a uniform distributed load. So a simply supported beam subjected to a uniform distributed load is loaded with what kind of internal forces? So shear and bending, but shear in plane or out of plane in this case? In plane, so in plane shear and bending, in plane bending, okay? So this means that now the situation is slightly different from before. It comes here. We have like, for example, a situation like this. And we have, we said, in-plane bending and in-plane shear. Okay. Now, I mean, this is looked in the other direction to make it simpler. Okay. So after we also saw this direction, but let's start with this way here. So we have the joists which are oriented in the other direction. Then we have the sheathing. So this one is like a simply supported beam between the two bracing systems. So we have a general bending moment and the shear. Now, let's go back to what we did before. This bending moment. Who is going to resist mostly to this in-plane bending moment? In this case? Which joist?
The first
This one?
and
Well, strictly speaking, also the other. But if you want to make a simplification, if you have a cross section like this, in a cross section like this, you can just assume that the bending moment will mostly be resisted by the top flange and by the bottom flange. And we can just conservatively ignore the other joist in between. Okay? So again, we will have a compression force, C, in the top, in the outer, and the tensile force in the outer joist, C, like before, equal to T, equal M, in-plane bending moment, divided by, I don't know, we call it B, for example, this distance. The breadth of the, what is it called here? What we usually say? Okay, let's call it D. Sorry, let's call it D. So we have the same as with your notes. D and D. Okay? So the bending moment is carried out by the outer joist. Conservative. And then the shear, who is going to resist the shear? In a cross-section like this, like before, mostly I would say the web. Again, here, strictly speaking, we have a parabolic distribution. But this parabolic distribution is very close to a uniformly distributed one. Okay, because if you look at the curvature of the parabola, it's not very important. So again, we can assume that all the sheathing is going to carry the shear force. Since the sheathing is not continuous, but there are some panels like this, not only the sheathing itself will be subjected to shear, but also the nail connections. Okay, also the nail connection between the sheathing and the blockage and the joist will be subjected to this in-plane shear. So we have to design for in-plane shear the sheathing itself and the nail connection between the sheathing and the framing, so the joists and the blockings. Of course, in this case here, it's slightly more complex to achieve the diaphragm behavior, because in this case here, as you can see, we don't have a continuous joist running in compression and tension. So what will we have to do in this case to achieve the diaphragm behavior? What do you think? It's not written here, but now we can discuss it. So in this case, how can I be able to transfer the compression, the tension in this along the outer edge? The outer edge I have blocking, there the joist, the blocking, the joist. The blocking is loaded parallel or perpendicular to the grain. So the blocking is loaded in which direction? Parallel to the grain. And the joists are loaded perpendicular to the grain. So how can we solve this problem? How can we get out of this arrangement a tensile strength? What would you do it? Yes. How can you transfer the tensile force along this edge here? Since you have this discontinuity between blocking and joist. Which way? Which kind of detail you could use to transfer tensile force along this line? Huh? I don't understand.
Nail connection.
Yeah, but nail connection between what? Is it easy to do a nail connection between this blocking and
the joist and the plywood panels?
Yes, but then you see, then there is a problem, because then you would need to transfer all the tensile force into the plywood panel. The plywood panel is very thin. So you would need you would need to transfer the whole tensile force into the plywood panel, which is not easy because it's very thin. Instead, what we have to do, we need to make a continuity here on this line. To make a continuity, like we did before with the hold-down straps. The first thing is, if this is a blocking, and this is the joist, blocking, joist. Since this is loaded, this will be loaded perpendicular to the grain. The first thing is to use a metal strap here, and some nail in this way. So basically the axial force is transferred through here and here, through this metal strap, and you just pass laterally above the joist. You don't go inside the joist because the joist otherwise is subjected to tension perpendicular to the grain. So again, it's better to leave the joist outside this kind of mechanism. Of course, the problem is that in tension this works, but we need to make it to work also in compression. Compression, this is loaded perpendicular to the grain in compression. So we need to make sure that this doesn't buckle in compression. In order not to make it to buckle, what do we need to do? If you want to make this to work in compression, if I leave it as it is, what will happen in compression? Of course, if we have some compression perpendicular to the grain, so this could squeeze, and then this one can buckle in this way. Okay? If we want to avoid this buckle, what can I do? Now I'm talking about the case where this is compressed. So now I remove this. So this was in tension. In compression, when it worked, compression, this may buckle. Want to avoid the buckling compression, what should I do? Well, I could add a nail here in order to reduce this effective length here. Okay? Better to put only one in order not to transfer any tension when this is subjected to tension. Okay? Because if I put more than one, I could transfer some of the tensile forces inside. Okay, so this is a kind of detail that we should do if we have a situation like this. Of course, when we design for the seismic in this direction, it's okay. When we design for the seismic in the other direction, we need to take into account that, of course, we have a situation like this. So the seismic action, by now you should know, it's the total force divided by the length of the diaphragm, and then of course, Vp, the shear, the plane shear is released by the sheathing and the nail connections, W times L over 2, because this is like the simply supported beam. And then again, the axial force in the outer edge is M over D, so WL squared divided by 8 times D. So what we did here, basically. Okay? So this is a photo traditional solution using eye joists and using plywood panels, as you can see. So, with light frame construction, what kind of buildings can we build? Well, first of all, it's suitable for residential applications, which means again, plants characterized by several walls. So if you want to build an open space, this is not the best solution. Because here we need to have many partitions, many walls that will become all structural. Okay? So for an open space, of course, we would have enough wall to take all the horizontal force. So it's okay for residential application. Many walls and short spanning floors. You can see here some photos. Usually, this is taken from Canada. Usually in Canada, the first floor, the ground floor, is made of reinforced concrete, and then the other floors, in elevation, they are made of timber. And this is an experimental test of 1, 2, 3, 4, 5, 6-story light frame building that was tested in Japan by an American team some years ago. So in this case, the maximum height is 5 to 8 stories. So 5-story if you are in a non-earthquake area, 8 stories if you are in a non-seismic area, and 5-story if you are in a seismic area. So for example, here in dell'Aquila, you can't really build a 10-story buildings using this kind of time. You can get up to 4 or 5 stories. I'm going to show you shortly a building out, 6-story buildings made with this kind of system, constructed in a similar situation as l'Aquila in New Zealand, in Wellington, which is the capital of New Zealand, and where the city is built right on the fault line, more or less like here. Even worse, I would say, because here the fault line is not really in the center, it's the line of the city. And you will see that there are lots of, well, there were lots of problems. You have to use lots of wood, so it's not so simple. So I would say, in l'Aquila, max 4 to 5 story in a high seismic region. Behavior factor, 4 to 5. Now, according to the current Eurocode 8, the Italian regulation is 5, but in the process of revision, the Eurocode 8, according to the current Eurocode 8 and the Italian regulation, it is 5, but in the future revision, the Eurocode 8 will be reduced down to 4, because 5 is a bit too much. And of course, if you use such a high value of the behavior factor, you accept that if there is a strong earthquake, hopefully nobody will die, if we have designed well, but at the end, it's very likely we will have to pull down the building, because it will be characterized by high severe damage. So 4 or 5 means that it's going to plasticize a lot, it's going to, at the end of that, the earthquake probably is going to be completely tilted, okay? And then we'll have to pull it down. Okay, so this is the test that I was mentioning before. This test was carried out, this is a light frame construction, was carried out on the strongest and biggest, largest shaking table of the world, which is in Japan. So it was carried out in July 2009 under this earthquake called Northridge, which is 0.74 G acceleration. I would say significantly stronger than the one we had in dell'Aquila. And so it was a good kind of test to do. So, of course, timber structures are very flexible, so you can see there are significant displacement. So, if during an earthquake you are on a timber building, you will shake a lot. You have to be careful that something doesn't fall down, not if you have, for example, shells or something like this, you will shake a lot. But usually the building doesn't break because it's very elastic, so you don't have significant problems. You can see also from the inner, so those videos are taken from the internet. So and this test revealed what we already knew before, lots of damage at the end of the earthquake, but no casualty. I mean, there was one person inside, rather than falling down from his or her chair, of course, could eat himself, but he would have died. Nothing, the structure didn't collapse. And this is what I wanted to show you before, an example of a light frame timber building built in New Zealand, and the capital of New Zealand, which is called Wellington, which is in the southern part of the North Island. And as you can see here, there is a fault line, so this is the city, and there's a fault line just going through the city. It's quite a significant fault line, it's quite a strong one, probably stronger than the one we have here. This is a photo of the city, so this is the fault line, and this is where the building was built. So you can see not too far away from the fault line. So for sure in a high seismicity region. So, in this case, the subject of this design was basically a house for the students of the university. So, kind of one kind of a residency for the students, characterized by several rooms with several walls. So no open space. So that was the perfect one kind of plan for using this kind of system. So here is a plan of the building. So the black one, you can see there are several rooms inside. The black walls are the walls that were considered as a structurally resistant, so the bracing wall of the system. But you see immediately that an arrangement like this was not very good for resisting torsion. So in order to get some torsional resistance, they had to have some steel K-brace. So steel K-brace are bracing systems like this. In order to get some torsional resistance, they added 3 steel K-braces along the perimeter in order to get some of the walls oriented along the perimeter and to get some torsional resistance. Some details. So, this is what we said before is called platform framing. In the platform framing, as you can see, there is a wall, lower wall, then there is a floor, and then the upper wall is basically supported above the floor. This is called platform frame. In the inner solution, then you can see what is called balloon frame. In this case, we have a continuity of the wall, and the floor is actually supported outside from the wall. So this is more complex to construct, but it's more effective in this case here. And at the right end, you have some platform framing with double wall, which is the most common for multi-unit development. So this is the detail that was adopted in this building. So wall, vertical wall with a sheet on one side. Then we have, you see, the floors are outside the walls, so they adopted a balloon framing in this case. So the joists are outside the wall, and they are not squashed by the load of the wall. Because here we are talking about a building which was 6-story high. So if we had a kind of platform framing, you would have probably some problem about the compression perpendicular to the ground. So in this case, we use the the balloon framing. And here, this is the continuity. You see that the sheathing must go through the walls in order to be able to transfer the shear forces from the sheathing of the floor down to the vertical walls. This is a photo. So studs, vertical studs, blocking, top plate. Then there is the bottom plate on the upper wall. And you can see that only the plywood is in between the two walls. Not like before, also the blocking. So for the platform framing, you would have that bottom plate, ply, you would have a blocking, and the top plate would be underneath for the platform frame. Then for the balloon framing, only the plywood is squashed between the two walls. This is another photo. So the studs, the plywood, those are some guides for later on to attach the gypsum plasterboard. To close here, and then here this is the joist of the floor. This is the K bracing that I was talking before. So this is diagonal K bracing here to provide some lateral resistance on the outer walls. You see, one of the problems, for example, was transferring the tensile force due to the earthquake down to the foundation. So those tensile forces were very high because we are talking about a 5-6-story building in a very high seismicity area. So they couldn't use only timber to transfer the tensile force down to the foundation. They had to add, you see here, basically a tube made of steel. So in the end, to transfer down to the foundation tensile force, we have to use one timber member, one steel pipe, and another timber member, all connected together with this bolt in order to be able to transfer the tensile force down to the foundation. So that's why I'm saying that to build a 5 or 6-story high building in a high seismicity area using this kind of system, it's a big problem. So probably not very economic. Again, photo, steel pipe, timber member, and bolts connecting the three of them together to make them to work together, because otherwise you would have only one of them working. So, in the end, they ended up with plywood sheathing 19mm thick, nails of 3.33mm diameter at 40mm center. So we have one nail every 4 centimeters, so 20 nails. The plywood thickness was reduced from 19mm to 15mm for the central two floors and 12mm for the upper two floors. And some numbers, they use solid timber, so another interesting thing that all this building here was made by using solid timber. So the size you see is 90 by 45 is what we call is a 2 by 4. So, sorry, it will be a 4 by 2. So this is in inches. It will be 2 by 4. That was used for basically everything. And they use 2,000 sheets of plywood and 500,000 of nails in the end to build this building. So if you look at the times, the timber structure started mid-February, you see 2004, and progressed at about 2 weeks per level. So 2 weeks to build one level, one story. In the end, this is the building at the end of construction. As you can see from outside, you couldn't recognize this made of timber because it is cladded by materials different by timber, so you can really guess that the size of the timber structure. So construction time, 4 months for the reinforced concrete foundation, so we'll have a kind of serious foundation to do, and 5 months for the timber bar. So if you look at the time, it's not much different from the time you would have used for a reinforced concrete construction. So 6 story, maybe with reinforced concrete you use 6 months instead of 5 months. So it's not a lot of advantages in terms of time using this kind of system. Because in this kind of system, the level of prefabrication was very low. So this was constructed according to the standard in Anglo-Saxon countries. Again, the only prefabrication was the bare frames. So the frames, what we were saying before, the only prefabrication was this bare frame that was delivered done in this way, and then it was cladded everything on the building side. So very little prefabrication. So, in Europe, we definitely use a higher standard of prefabrication, also higher standard, I would say, of finish. So right now, in Europe, we would never construct a building like this in this way. So the typical example are those panels that you can see here, and those photos are taken from one producer, House, which is one of the largest producers of timber building in Italy. I would say in South Tyrol, or in Italy, but still Italy anyway. And in this case, the idea is that, but not only that, all the other Italian producers have the idea that in order to improve the construction, to reduce the cost, they try to prefabricate as much as possible, to build as much as possible in the factory, and then to go to the building site just to assemble those walls together. So, and as an example, this is taken from House. They start from a detailed blueprint. So this is the blueprint of the structure. This is a real blueprint, so real, I would say, Italian progetto esecutivo, with all the dimensions in millimeter and everything's there. And then this design here is going to, in some way, it's going to be read by a computer, which is connected with an automatic machine to produce the frames. So you can see here in this machine, based on this project here, they produce the frame. There is also a component, of course, not everything is fully prefabricated, there are also some men helping. And in the end, you see this, all the pieces of timber are cut to size based on this blueprint. Then the frame, the bare frame, is prefabricated using some automatic nailing machine. So you can see here the bare frame using this produced by the workshop. Then again, the sheathing are placed on top on one side of this framing, and again the nailing is carried out automatically. And then this frame, it moves to another section of the factory, and you can see that also this frame is equipped with some plants. For example, here we have electrical pipes, we have hydraulic pipes for the toilet, and so on. Then it is cladded. Here you can see during construction the different phases of the cladding. And in the end, even the windows are placed and doors. So the whole wall with all the plants is basically shipped with a lorry and sent to the building site. And to the building site, the only thing they have to do is then just to connect together the walls with some special connections Same thing for the floors. Also the floor panels are prefabricated. And they are usually used for floor panel, used for facade, so everything is prefabricated. And the idea is that in this way, the time on the building site is reduced to a minimum. Okay, so in Italy, I would say in Europe, you will always find, in this time, you will always find prefabricated, highly prefabricated light frame construction. Just a reminder that with this kind of the structural type, as I said before, you cannot go as high as you want. The limit is 4 to 5 story in a high seismic region, 7 maximum in a non-seismic region. Okay, now we go to the next structural type, which is the solid panel construction. Solid panel construction, unlike light frame construction, it's a continuous kind of panel. So in this case, the panel is continuous, it's heavy. Of course, it's always lighter than reinforced concrete because it's made of timber, but it's heavier than before. So the materials that are used in this case are cross-laminated panel. This is the largely used material nowadays for solid panel. Also glue laminated slabs, and also laminated in a lumber, which is not much used in Italy. And they can also be used in combination to create a heavy solid panel. As I said before, cross-lam is by far the most used solid panel construction material nowadays in Italy and Europe. The idea in this case is that those panels can be used for the walls, and when used for the walls, they need to be connected together, because of course we have to connect a number of panels together. So the typical connector used to connect these cross-lam walls are hold downs. So those are called hold downs. The hold downs are steel plates like this that are nailed on the wall on one side, and they are connected on the foundation using some bolts on the other side. Let's say, for example, in this case, they use 4 millimeter diameter nails times 60 millimeter long to connect the plate with the wood. The hold downs, like the name suggests, are needed in order to hold down, to take down the panel, so to resist the possible uplifting tensile forces due to horizontal forces. So if we push on top of the panel may tend to rock, may tend to rotate, and so the hold down is needed in order to prevent this rotation. So in other words, what we are talking about right now is that this is a panel, cross-lam panel. We apply axial force here. So due to this axial force, the panel may basically rock in this way. And so here we need a hold down to keep the panel down, basically. So to resist to these tensile forces due to uplifting and due to the rotation due to this horizontal force. So this is hold down. So the hold downs are always placed at the end of the panel. So where they are at the end of the panel. Then we have what we call angle brackets. Again, made from metal plates, which are connected to the wood using again nails, and can be connected to the foundation using some bolts. The angle brackets instead are needed in order to prevent horizontal displacement, so slip of the panel itself. So the angle brackets are there to prevent translation, this kind of movement, horizontal movement of wall themselves. The under brackets are usually placed in the inner part of the wall at a constant spacing to each other. So those under brackets are there to resist to shear. And then, if the wall is made from different panels, because for example it's a longer wall, then we have to connect the walls together using this kind of joint. For example, this joint here we have some LVL, so strips of LVL, so looking down, the wall is carved in this way. So those are the two panels. And then, in this carving here, an LVL strip is used, and this LVL strip is connected with the two walls using some screws in this way. So, for example, self-drilling screws used to connect the adjacent panels, 8mm diameter and 80mm length. So, this joint here is used in order to transfer the shear forces between two adjacent panels. Okay? So, typical X-ray panel construction, we start by placing the walls together. So the walls are connected to the foundation, we said using all downs and the brackets. Then they are connected together using these LVL strips and the screws that have been designed to resist shear. And then you see at the corner, or the intersection between different walls, some other self-drilling screws are used in order to keep the walls together to prevent the opening of the wall. So the idea is that this structure should be held like a kind of box structure. In a box, what we need to complete the box is after this one. We want to make this one as a box, what do we need now? We need to put a floor on top, the roof of this box. So in fact, you see the next stage is to cover this box, to create the box, to put some strips of floors again. So those strips of floor are connected to the walls using self-drilling screws, and are also connected together with this kind of joints. So if this is one panel, one strip of floor, and this is the other strip. And here again we have some screws. So the panels are connected to each other using these screws, and then they are connected with some other screws to the vertical wall, inner and outer wall. So this, as you can see, this is like a box. It's a real box. So it's extremely strong. The structure here is very, very strong. So just a reminder, of course, that this box, in this box, the weakest link is that connection. So usually, it's very hard to break one of those panels. Usually, what breaks first is the connection. So the connections are the weakest link in this kind of box structure. And then we proceed by, again, placing, you see, on top of the floor. So again, this is what we called before. This is again another example of platform construction. Because you see that on top of the floor, we place other walls. And then another floor, and then another wall, and so on. So the floor themselves, the floor panel, are squashed between the supporting wall and the wall on the top of the floor. So in the end we get, as you can see, a very strong structure by using this kind of system. This is an example. Very often, in order, again, to take advantage of quick fabrication, the whole wall is already cut, arrives on the building side with the opening already cut. So, again, you see the place there. You see also here some temporary bracing. Why do we need this temporary bracing? because those temporary bracing are needed until we place the floor on top of it. So without, let's say that this structure for sure is less stable than the one we saw before, but nevertheless it's not completely stable until we don't place on top of the wall the floors, so the floor panel, in order to complete the box. So this will be as stable as a box without the cover. As you know, a box without the cover is not very stable. When you put the cover on the box, it's much more stable. Okay? So for this reason here, some temporary bracing can be used. Another photo. Okay, this is an interesting example. So this is the use of cross-lamp system for an extension of an existing hotel. So here we are in Val di Fassa, I think, Fassa Valley, which is the Dolomite region, where the owner of the hotel wanted to enlarge the hotel. This was some years ago, when we didn't have the crisis like now. And the idea was the owner wanted to be able to have the hotel open until Easter, because until Easter on the Dolomite you can ski. And then he wanted to be able to have some guests starting from June, because then, of course, until Easter you go skiing, and from June you go walking or relaxing the mountain. So he had available 1 month and a half, because Easter, that time was, let's say, half April. So in 1 month and a half, he wanted 1 month and a half to be able to do this extension and then to reopen the hotel. With the normal system, if you do an extension even out of reinforced concrete, we were talking about 3 floors, that wouldn't be impossible. So one of the reasons why he chose the cross-lamp system was also this, because as you can see in terms of timing, we are very fast. So to construct the first floor, 2 days of work. Then to construct the second one, other 2 days. Then the third one, other 2 days. And in the end, to get to the roof, 10 days. So, very fast. Yes?
Ma in fase di cantiere, in queste situazioni, se ad esempio dopo 2 giorni c'è una nevicata.
No, but he was talking about the spring. We were talking about end of April. You look around here, there is no snow anymore. Anyway, it's not, even if there was a snowfall, it wouldn't be so critical. The important thing is that if you get a timber panel, you can also get some water or some stuff. Snow installation is better snow than rain, of course. As long as the snow doesn't melt down, of course. But the problem is that if these panels get wet, it's not a big problem. The problem is after they need to be allowed to get dry. So the worst thing that it may happen to a timber structure is that it gets wet and then it cannot dry anymore. Then you have lots of problems here. Okay? So, we said before, 10 days work to get this structure done. Of course, it's not everything completed because you still need to have the finishing and so on. But compared to reinforced concrete, for sure you are able to do this extension in 1 month and a half. It was the target of the owner. Okay, this is a video taken in Graz. So Graz, there is a university, the Technical University of Graz, which is very famous for cross-lamp. So this guy here called Schickofer, he basically did his PhD 20 or more years ago on cross-lamp, and after that he just did lots of research on cross-lamp. So he basically was focused almost the entire life on studying cross-lamp. In fact, he was also awarded a kind of prize similar to the Nobel one, but because you know the Nobel Prize is for physicians, it's not for engineers or for politicians, like Obama and so on. Instead, for the engineer, there's another prize with another name. They got this prize for his work on cross-lamp. Now, this video, you can see here, now we just start the video, you can see the construction, of course, accelerated a little bit, because otherwise we don't have lots of time. How the construction proceeds for a building like this, which is a typical residential building. You can see also, you can count how many nights here. You can see that the 3 stories in 6 days they are more or less completed. You can see that in this case there is this lift and stair shaft made of reinforced concrete. Why is that? Because in Austria, so far, there is a fire regulation which does not allow to have combustible structures in the egress system, which means in the Bierfuga, no? Which means staircase and lift shaft. In Italy, such a regulation does not exist. So in Italy, we can, if you want, we can build the whole building out of wood without the need to have a part made of reinforced concrete. So again, this building size is completely different, much cleaner and easy, if you want, easier to manage compared to a typical reinforced concrete building, because you don't have to pour or to cast concrete, so it's completely different situation. And as you can see, it's very fast. I mean, because the whole panel is prefabricated, you just put some screws and that's it. It's really simple. So. This is the typical detail, so floor wall details of a floor slab system. So this is the panel, this is the wall. Then you see, due to some problems about the most, I would say, acoustics, if you want to get the acceptable acoustic separation, you cannot have your parquet directly on the timber, but we need to use some sand and then some non-structural concrete in order to get a better acoustic separation. And then you can have your parquet. Gypsum plasterboard, and then you see here some thermal insulation using cord fiber of wood fiber. Unfortunately, fortunately, in my opinion, most of the concrete you can see now in Italy is not actually coming from Sardinia, but it's coming from Portugal. For some reason, the Sardinian producer cannot enter very easily in the Italian market. I don't know why. At least not for this kind of market. So, we said before, all downs and under brackets. Here, this is kind of metal tools that we use. So, all downs, under brackets, self-drilling screws, self-tapping screws, nails and so on. Of course, those screws are self-tapping screws, so you don't need to do the free bore. You can just use the screw directly. And then here you can see different details to connect the cross-arm wall to the foundation. So we can use all downs and angle brackets, or instead of the angle bracket, we can use inclined screws. So we will see more and more inclined screws because, as we already mentioned, talking about connection, inclined screws have the advantage of being very stiff. So you can reduce the number of screws if you use inclined screws. Different kind of joints between bolts. You can see this is what we showed before. This is also the standard version, or this is used for the floors. The self-drilling screws. And then, of course, when it comes to design wall, as I said before, most of the design of cross-slab buildings is actually the design of the connection, not the design of the wall, it's the design of the connection. So, if we have a wall which is part of the gravity load resisting system, part of the lateral load resisting system, we can assume that this wall will be subjected to a vertical uniformly distributed load, QVD, coming, for example, from the floor or coming from the other walls. And then it will be subjected to a lateral force on top, so this is THD. So the hold downs are calculated, as I was saying before, to prevent uplifting. So in order to design the hold down, we basically calculate the bending moment with respect to this point. So, okay, well, if you want to find FTD, we calculate the bending moment with respect to this point here. So this would be THD times H minus QVD times B divided by, sorry, times B divided by 2, because this is the bending, it's a positive, the stabilizing bending moment of the axial force. So, THD times H minus QVD times B divided by 2 minus FCD, minus minus FTD times B equal to 0. In the end, from this equation, you get that FTD, so the axial uplifting force in the all down will be the bending moment, the destabilizing bending moment, so THD times H divided by B, minus QVD times B divided by 2. So this is the strength demand in the all down. Of course, the strength demand should be less than or equal to the strength capacity of the all down. And then we need to take into account the strength demand into the under brackets. The under brackets are assumed to resist only shear. So FSD, strength demand in the under brackets, will be the total shear divided by the number of under brackets. Very simple. And this shall be less than or equal to the desired strength of the under brackets. How do we design the vertical connection between adjacent wall panels? For example, assume that you have a longer wall made of two cross-slab units. So on top of the wall we have this horizontal lateral load, THD, and then of course we will have a distribution of shear forces along the top side, so THD, and then we have also distribution of shear forces along the vertical joints. So we are interested in finding out the value of TVD, which is the desired shear forces acting in the vertical joint. So FTD will be the uplifting axial force in the all down, will be the same as the compression force in the other all down. This will be the bending moment, so THD times H divided by B. Now, if we study the equilibrium of the vertical forces from the part A of the wall, so only consider that's this part of the wall, we can write down that TVD, so the tangential force in one side of the two parts times H, so the resultant of this vertical force shall be equal to FTD. So for the equilibrium of the vertical forces, this one here, FTD will be the same as TVD times H. So TVD is FTD divided by H, but FTD is also THD times H divided by B. So in the end, it's also THD divided by B. Now we do the equilibrium of the horizontal forces. So THD is tau HD is THD divided by B, and this is equal also to TVD, because the same formula as before. So in the end, one single screw in this vertical joint will be subjected to a shear force, FED, which will be TVD, the shear force, times the spacing of the screw. So in the end, if we replace with the value we saw before, it's THD times S divided by B. And this shall be less than the resisting strength of a screw, which would be normal formula, effective number of screws divided by the number of screws, because they are aligned, one line parallel to the grain, times K mod times FRK divided by gamma over FRK is taken from Johansen equations. So, in terms of X-lam panel construction, so cross-aggregated panel construction, we could say that those kind of systems are suitable for, again, residential buildings with several walls and medium span floors. So again, this system is perfect, like light frame construction, if you have a building characterized by several divisions, several walls. So again, residential application, certainly not office or open space applications. In this case, we can go a little bit upper. We can get to up to 7 floors, 7 stories. The Q factor in this case is between 2 and 3, so it's lower than for the light rail construction. At the moment, according to the Eurocode 8, there is no provision for X lambda. We could say that we use 2. But some experimental tests performed within a project or SOFI project show that we can get up to 3 as the use of behavior factor. Some tests show also an excellent seismic performance with limited residual damage at the end of the seismic event. So the advantage of this system is that, if you want, unlike industrial construction, the experiment showed that at the end of the earthquake, the building was not so damaged to be tilted in some way, but it basically snapped back in the position, the vertical position where it was before. One disadvantage we're going to see anyway is that the system is quite rigid. It suffers quite a lot from strong earthquake, in the sense that the accelerations, if it happens that you are on the top of one of those buildings during a strong earthquake, you will shake quite a lot because we found very high acceleration on the top of a building. Like this. So this is a test that was carried out. You can find all this video on the internet. Maybe some of you have already seen this video. So this is the shaking table test carried out in 2007 within the SOFI project. Again, the same shaking table. The shaking table is basically, I didn't tell you before, the shaking table is basically a device like this that can replicate exactly the effect of an earthquake. So it can move exactly like an accelerator, to reproduce exactly the same earthquake that had been recorded somewhere. In this case, so this was a 7-story building that was built out of crossland. This was within the project called SOFI project. The principal investigator was Professor Cecotti, former professor at first at the University Institute of Architecture of Venice, and then director of CNR Ivanza in Trento. So they had the opportunity to do this quite interesting project, this very big building that was built on this shaking table. And this was shaped using this Kobe 3D earthquake. So this Kobe was a very strong earthquake that occurred in the past. As you can see, 0.6 G acceleration X, 0.82 acceleration Y, 0.34 acceleration vertical. So very strong, if you think, because now when we talk about, for example, the dell'Aquila one, the value were quite small compared to this. So this one was a very strong, was the penultimate strong earthquake occurred in Japan. Was not the last one. The last one was after this, was the one where we had Fukushima. One before was this. It's quite strong. So, this video, we can show the video starting from the one from outside. And again, you can notice that there is quite a significant movement on top of the building, because again, timber has a problem of being very low modular of elasticity, meaning that we have very strong displacement, as you can see. Now we'll have another, we will concentrate just on the top. So quite flexible. Despite the fact that this is actually, it's a rigid structure, but still subjected to significant fluctuations due to the earthquake. Then maybe it doesn't seem so, but if you look from inside you will see that the acceleration is quite big, it's quite strong. So it's clear that if you occur to be inside during an earthquake like this, for sure you will fall down, because of course nobody can know that an earthquake is coming, so it can brace itself. So for sure you will fall down, and maybe you may suffer from some problem. Because the acceleration, the recorded acceleration on top of this building was something like a 3G, but for a very small, for a millisecond. So 3G, just to understand, 1G, if you do what's called bungee jumping, or you just go parachuting, when you throw down yourself, at the beginning the acceleration is 1G. You throw in a free fall down here. This is 1G. So 2G or 3G means that it's quite strong. So you can't really, if you don't brace yourself, you can't really resist the acceleration of 2G or 3G. The good thing was that 3G was only for a millisecond, but still significant amount of acceleration. In fact, I would say that the only real problem with this building is the very high acceleration that can cause some damage induced by the fact that one person may fall down, or you may get a lamp or some books on your head. This is a real problem. But the building itself didn't suffer any kind of significant damage at the end of the earthquake. Okay, now I think it's not the time to start this one. I just mentioned that this is a very significant, very interesting example, because this building here was the first tall timber tower. Medium tall timber building being built in UK, in London. So this was built in 2008 or in UK, and after this construction, CLT became more and more common all around the world. So in some way, if you want to innovate something, you do your first building in London, and then you are sure that after that you will see more and more buildings built around the world, because in some way London, for this reason, is the kind of place where the innovation, once it starts there, it will spread out all around the world. Also because London has lots of connection with Australia, China, all over. But this is another story. I would like to discuss about this on Wednesday. Because this building here originally should have been made of reinforced concrete. And then for some reason we are going to discuss next time, the investors, client, decided to swap from reinforced concrete to timber. So now a question for you. Do you think that did he decide for global warming or sustainability? They went to timber? Yes or no? Yes. Originally this building was supposed to be made of reinforced concrete. And then the client, the investor, the owner, decided to swap from reinforced concrete to timber. Now my question is, did he make this choice for sustainability reason, for global warming, in your opinion? Just an impression, what do you think? It could be. But I can tell you this was not the main reason. The reason was economic argument. So next time, tomorrow, the day after tomorrow, we're going to discuss why a building like this made of timber. Actually, timber, all these panels, that's the interesting thing. These panels were all imported from Austria. So UK at that time, they didn't know anything about Prussia, so they had to ship all the panels all the way through Austria with lorries down to UK. So this seems strange. No, they don't have the material, but despite the fact that they were going to spend more because they had to import, they didn't have the material to buy from Austria to import that, they actually decided to do this choice to make this way, not for sustainability reasons. Okay. I hope you can sleep also without knowing this answer. But we are going to discuss more, I'm going to tell you more on Wednesday, because this is a very interesting story. Okay, thank you, and we'll see you.